Today's lesson, section 4.6a, we are modeling with exponential and logarithmic functions. So, most of these will be exponential functions that we deal with for modeling situations that actually certain careers deal with on a regular basis. So, exponential growth, specifically doubling time, would be if the initial size of a population in n sub 0 and the doubling time is a, then the size of the population at time is n sub t, which equals n sub 0 times 2 to the t over a power. Okay? Where a and t are measured in the same time of units. So minutes, so they both need to be minutes, or both hours, both days, years, whatever. Okay, so just make sure that they're both the same, because sometimes in your equations or word problems they'll give you one in one measurement and another and then a different one, so you need to adapt one to the other or vice versa. Okay, so example 1 says, under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in a day. So find a model for the bacteria population after t hours. So that means when they do this first part, they just want you to write the equation. Okay? So letter A is looking for n sub 0 or n sub t. Sorry, n of t, and so our initial, so that n sub 0 is going to be the 1,000. Okay, and then we're looking for t and a, what those would be, right? Okay, so remember that t is our time. Now, usually that's the variable, so times 2 to the t over, and then a will be the value that we were doubling by. So we're doubling every 3 hours. So then we're going to put over 3. Okay? So here that would be my formula or my model that would represent this. So letter B now asks how many bacteria are in the colony after 15 hours. So then that means that t is equal to 15. So n of 15 is equal to 1,000 times 2 to the 15 divided by 3 power. So when I simplify this, that gives me 5. And 2 to the 5th would be 32. So then that gives me 32,000. Okay? So that would be the answer to letter B. Letter C says, when will the bacteria count reach 100,000? So there, they're telling you the n population. So they're saying n of t is equal to 100,000. So then we insert that in. And then we want to use our equation solving skills to help us find t. So first I need to get 1,000 to the other side because I want to isolate my base. So 100,000 divided by 100 or 1,000 would be 100. And so then now I want to take it to the log to both sides. So log of 100 equals a log of 2 to the t over 3 power. Now I can use my power property and move the t over 3 down. Okay, and so now I want to move my log of 2 to the other side. And also I need to move my 3 to the other side. So I can divide by log of 2. Now a nice thing here is one of your options is using your other properties. So remember, this is common log, so 100 is the same thing as 10 squared, right? So then, remember, I can cross out those 10s, and it leaves me with 2 because of my properties. So now I could say 2 over log of 2 is equal to t over 3. And then I want to multiply both sides by 3. So that gives me 6 over log of 2, which is equal to t. So if I plug that into my calculator, t should equal 19.93 hours. Okay. Now, next one is just a general exponential growth. So exponential growth is just meaning relative growth rate. So this could be any value, but we usually now we're going to use our base of e instead of a base of 2 because it's talking about the exponential growth. So a population that experiences exponential growth increases accordingly to the model of n of t is equal to n sub 0 times e to the RT power. So it's very similar to our compounding interest or continuously compounding interest problem. They work kind of the same way. So n of t is the population at time t, n sub 0 is the initial size of the population, r is the relative rate of growth, and then t is time. Okay? So here, for example 2, the initial bacterium count in a culture is 400. The relative rate of growth is determined to be 20% per hour. We want to find a function that models the number of bacteria after t hours. What is the estimated count after 1 day? And what will the bacteria count reach at 100,000? Okay? So first I want to write my equation or my function. So n of t, my initial count of that culture is 400 times e. And so because I said 20%, remember I got to convert that to a decimal. So that's the same thing as like 0.2. So 0.2 and then that times t, which is time. So there's my equation. So letter B wants to know when will or how many will happen after a day. So since we're saying in hours, that means that I need to plug in hours for a day. So I convert that to 24. Okay, so 24 is the time that I plug in. So 400 times e to the 0.2 times 24 power. And so here actually I could probably just plug that into my calculator, and that will give me 48,604, and it gives you 0.7. But here you can't really have, since we're talking about bacteria, you can't really have 0.17 of a bacteria. So usually for bacteria we round down, so we don't overcount. Okay, so then that would be my answer. Letter C wants to know when will the bacteria count reach 100,000. So same properties apply. So kind of like the last problem. So I have 100,000. I set that equal to 400 e to the 0.2 t power. I want to solve for e, so divide by 400. So 100,000 divided by 400 would be 250. And then from there, now because I have e, the last one I had bases of 10, so it was good to use common log. Here I want to use ln because I have a base of e. And that will cancel it out. Makes it a little easier for my math. So ln of e goes away, so ln of 250 is left with 0.2 on the other side. So now I want to get t by itself, so I'll divide both sides by 0.2. So t will equal 27.6 hours. Okay? Now the next one, Now we can kind of go the other way. So instead of growing, we can decay. So radioactive decay model would be next. So if m sub 0 is the initial mass of a radioactive substance with half-life h, then the mass remaining at time t is modeled by the function of mt is equal to m sub 0 times e to the negative rt. So notice that our rate, it would be negative. Now to find r, we take ln of 2 divided by h. Okay, so h is that half-life, or so how long it takes to become half of what it is. So for example, 3, talking about polonium, hopefully I said that right, 210, and there's the abbreviation for it. So it has a half-life of 140 days. Suppose the sample of this substance has a mass of 300 milligrams. So letter A wants us to find the function using the general model. Letter B wants us to find the mass remaining after 1 year. And then letter C wants to know how long will it take for the sample to decay to a mass of 200 milligrams. Okay, so just like the A for all these, I want to write the general form for this. So I'm starting with an initial amount of 300 milligrams. So that's what I'll put in for m sub 0 times E. Now I need to find R. So R will equal ln of 2 divided by the half-life, so 140 days. So that value actually rounds. Now you can do one of two things. You can use this value, which is perfectly fine. It's not as exact because I'm rounding a decimal. Or I can just plug this in for my R and just say negative ln of 2 over 140 times t. Okay? Either one's fine. But I would prefer that one because you get the most exact answers from that. Okay? So now, if you want to know how much will be remaining after a year, remember 1 year, we want it all in the same time units. So 1 year would be 365 days. So then I plug in 365, 300 times e to the negative ln to 140 power times 365. Okay, so I want to plug that first number in. So let's find negative ln 2. Notice that the negative is on the outside, not the inside with the 2. Divided by 140. And then take that times 365. So that gets me roughly negative 1.807. Now remember, leave that in your calculator. Take second e to the second answer power. It gets me about 0.16, and then times 300. So then here, I get 49.237. And so because we're talking about the mass, now since you're talking about milligrams, you can have a decimal in milligrams. Let's round it to the nearest hundredth though. So 24 milligrams. Okay. Letter C wants us to do the reverse, kind of like the other ones we're having us do. So instead of 100,000 though, I want to see when I'm going to get 200 milligrams. So then I set that equal to 300e to the negative ln 2 divided by 140 times t power. So here I'll divide by 300. So it gives me 2/3 when I reduce. Okay. And then now I want to take ln of both sides. Okay, so that gets rid of the ln of e part. So you're left with ln of 2/3 equals negative ln of 2 divided by 140 times t. So now I could multiply both sides by the reciprocal of that fraction, which would be negative 140 over ln of 2. So then now t will equal, so that get us 81.89 days. For our t value. Okay? So that's kind of how we're working with exponential functions. So they're going to kind of ask you similar questions for your problems. Okay? Have fun.